Welcome to today's Explainer. I am so excited to be your guide as we dive into a seriously fascinating topic, the structure of crystalline solids. Basically, we're going to look at the microscopic architectural blueprints of the materials that make up our entire world. Have you ever stopped to wonder why a piece of metal behaves the way it does? You know, why it has a specific weight, or why it bends under pressure instead of just shattering? Well, the answers aren't found on the surface. They're hidden deep, deep down within the atomic arrangements. So let's jump right in and decode how these tiny building blocks totally dictate the properties of the materials we rely on every single day. Here is our roadmap for today. We'll kick things off with crystals, order from chaos, then move into metallic crystal structures. After that, packing and density calculations, navigating crystals using Miller indices, and finally, seeing atoms with X-ray diffraction. Let's get to it. Quick question for you to keep in the back of your mind before we start looking at the structures. Think about the metals you interact with all the time. The steel in your car, the aluminum in your phone, the copper wiring in your house. What actually determines their density and their overall stability? What makes one dense and super strong and another one lightweight? Keep that central mystery in mind as we explore our first set of structures.
Okay, Section 1. Crystals. Order from chaos.
So, the materials all around us generally fall into two broad camps based on how their atoms are arranged. On the left side, we have crystalline materials. This includes your metals, a lot of ceramics, and even some polymers. Their defining feature is order. Their atoms are arranged in these perfectly periodic three-dimensional arrays. It's highly predictable. But on the right, we have non-crystalline, or amorphous materials. These completely lack any sort of periodic arrangement. This usually happens because of really complex structures or from rapid cooling. Like if you rapidly cool liquid silica, you get non-crystalline glass, rather than giving it the time it needs to slowly form a nice, neat crystalline structure. And this right here brilliantly illustrates exactly why metals prefer to be crystalline in the first place. Take a look at these two graphs comparing non-dense random packing to dense ordered packing. The top blue curve shows random packing, while the red curve below it represents ordered packing. Notice where the lowest point, that little dip, is on each graph. That dip represents the absolute minimum in bonding energy. The crucial takeaway here is that dense, ordered structures reach a much deeper minimum in bonding energy. Because they sit nearer to that minimum, they are just fundamentally more stable. Nature absolutely loves stability, and that is exactly why metals organize themselves into these tight, highly organized crystalline blueprints.
Moving right along to Section 2, Metallic Crystal Structures.
Now, before we start looking at the actual shapes, we need to quickly define the rules of the game. When evaluating a crystal structure, material scientists rely on two absolutely key metrics. The first one is the coordination number. Simply put, this is just the number of nearest neighbor or touching atoms that surround any single atom in the structure. The higher the number, the more crowded the neighborhood is. The second metric is the atomic packing factor, or APF. Assuming our atoms are little hard spheres, the APF is the volume of the atoms inside a unit cell divided by the total volume of that entire unit cell. It gives us a strict, cold, hard number telling us exactly how efficiently the space is being utilized.
First up in our structural gallery is the simple cubic, or SC structure. Now, what's kind of wild here is how relatively empty this structure actually is. In a simple cubic setup, atoms are located solely at the 8 corners of a cube. Because every single corner atom is shared by adjacent cubes, this unit cell essentially contains exactly one full atom. When you run the math for the atomic packing factor here, you get a measly 0.52. That means 48% of this structure is literally just empty space. It's like a horribly packed suitcase. Because it has such a terrible packing density, you'll find this structure is actually super rare in nature for metals.
Let's step it up to a much more common structure, body-centered cubic, or BCC. Notice the distinct difference right away. We still have our atoms at the 8 corners, but now we've got a single, full atom sitting right smack in the middle of the cube. If you look at that center atom, you can easily see that it touches the 8 corner atoms all around it. That gives BCC a coordination number of 8. This specific structure packs space a lot more efficiently than the simple cubic, and it's the go-to blueprint for metals like chromium and alpha iron.
Okay, let's see how this builds up to an even denser setup. Face-centered cubic, or FCC. This perfectly shows how FCC is created by stacking close-packed planes of atoms. Look closely at the stacking sequence diagram. It follows a really neat ABC-ABC pattern.
The bottom layer is A, then the next layer B sits perfectly in the little hollows of A, and then the third layer C sits in the remaining hollows before the whole pattern repeats itself. This beautiful overlapping geometry gives us an incredibly efficient APF of 0.74. That means 74% of the volume is solid atom. It also bumps our coordination number all the way up to 12.
We're going to conclude our gallery with the hexagonal closed-packed structure, or HCP. Now, HCP is fascinating because it actually ties for first place in packing efficiency. Just like FCC, it boasts an impressive APF of 0.74 and a coordination number of 12. But visually, the geometry is totally different. Instead of a cube, it forms this hexagonal prism, and instead of an ABC stacking, it uses an alternating AB-AB stacking sequence. The middle layer sits perfectly nestled between the top and bottom hexagonal layers. This is the structural foundation for metals like cadmium, magnesium, zinc, and titanium.
All right, Section 3, Packing and Density Calculations.
Don't let the math scare you here. The theoretical density equation you are looking at isn't magic. It is just simple logic. Theoretical density, which is represented by the Greek letter rho, is exactly what it sounds like. It's just the total mass of the atoms inside a single unit cell divided by the total volume of that specific unit cell. Seriously, it's just the microscale version of the classic density formula you probably already know, mass over volume.
Let's break down those variables so the algebra is completely digestible. To find the mass, we take n, which is the number of atoms per unit cell. Remember, that was 1 for simple cubic and 2 for BCC. And we multiply it by A, which is the atomic weight of that specific element. Then we divide that by Avogadro's number, n sub A, to get the mass of just those few atoms. Finally, we divide that entire mass by VC, the volume of the unit cell itself, which is usually just the lattice parameter cubed for our cubic structures. By directly tying n and Vc back to those 3D shapes we just explored, we can mathematically perfectly calculate the real-world density of a material.
Moving to Section 4, Navigating Crystals, Miller Indices. To prove that mapping these crystallographic planes is a highly logical and predictable process, let's walk through exactly how to find the Miller indices. Step 1, establish your origin. If the plane happens to pass right through the origin, just move your origin to another unit cell. No big deal. Next, read off the intercepts where the plane actually crosses the x, y, and z axes. Then, take the reciprocals of those intercepts. This is actually a super clever trick to handle planes that run parallel to an axis, so you never have to deal with the math of infinity. After that, normalize those reciprocals by multiplying by the lattice parameters, then reduce them to the smallest possible integer values. And finally, enclose the resulting 3 numbers in parentheses, like 1, 1, 0, no commas. It is such an elegant universal language for navigating these crystal structures. Which brings us to our final stop, Section 5, Seeing Atoms, X-ray Diffraction. We've built the models, we've done the math, and we've mapped out the plans. But we have to ask a critical question right now. How do we actually measure these microscopic plans in the real world? We certainly can't pull out a tiny ruler. The distances between these atoms are unbelievably small, literally on the scale of nanometers. So to gracefully transition from our mathematical models into physical reality, we need a tool that operates on the exact same wavelength as the atoms themselves.
And that tool, my friends, is the X-ray. Let's look at how this perfectly illustrates Bragg's law. Follow the incoming X-rays. You've got wave 1 and wave 2 hitting the crystal structure. Wave 1 bounces right off the top plane of atoms, but wave 2 penetrates a little deeper, bouncing off the second plane down. Because wave 2 goes deeper, it has to travel an extra distance before reflecting back to the detector. Bragg's law mathematically relates that extra distance to the angle of the X-ray and, crucially, to the spacing d between the planes. By carefully measuring the angle where the reflections are perfectly in phase to create a strong signal, we can compute the exact interplanar spacing. It's totally brilliant.
And here is the magnificent practical results of all that theory. What you are looking at is a real-world X-ray diffraction pattern for polycrystalline alpha iron, which we know from earlier is a body-centered cubic metal. See those huge spikes on the graph? They correspond to very specific diffraction angles. Notice the numbers labeling those spikes? 110, 200, 211. Those are the Miller indices we just learned how to calculate. The machine is physically confirming our mathematical models. Each peak means X-rays are bouncing perfectly off those specific microscopic planes within the iron's unit cells. It's absolute real-world verification of our atomic architecture.
To wrap up our explainer today, I want to leave you with a final, kind of provocative thought about what all this means on a macro level. We've seen just how rigorously structured these materials are. For most single crystals, their physical properties actually vary depending on which crystallographic direction you are pushing or pulling on them, a concept we call being anisotropic. If the shear strength or the electrical conductivity of a single crystal changes based purely on its microscopic orientation, how does that alter the way engineers design and build our world? When we use polycrystalline materials with randomly oriented grains, they luckily become isotropic, uniform in all directions. But it really just goes to show you, mastering the absolute micro is entirely the key to engineering the macro. Thank you so much for joining me, and keep exploring the blueprints of our world.